Lesson 39 activity. Make sure you read number 1, pause the video and do that now if you haven't done so already. We're moving on to number 2. We're going to first find the average of v of 0 and v of 35. To find the average of two numbers, we just add them up and divide by 2. So we're going to use our calculator to do this. This is not a calculus question. Okay, so we'll go into y equals and type in our function, 225 times 1.15 to the t, to the x. Okay, and then we'll come out here and we're going to do variables and then y variables and then function and then function. So y of 0 plus y of 35. Okay, so that's the total of those two values, and then we cut it in half to get the average value. So about $15,094. Okay, let's take a look at the picture. So 15,094 is the average of the starting value of this Tiffany lamp, which is right there, not very much, and the ending value after 35 years. So I'm going over here to 35. Where's 35? Right in the middle there. So we're going up to here-ish, and then coming over to here-ish. And we are taking the average of those two y values here, and it's basically 15,000, but it's just a hair over 15,000. And so 15,000 is like 15,094 is like there. And so the question is it fair to say that over the course of these 35 years, the average value of the lamp was $15,094? And I'm hoping you say no, because look, for almost the entirety of this 35-year period, up until here, the value of the Tiffany lamp was decidedly less than 15,000. For 30 of the 35 years, the Tiffany lamp was less than 15,000. It was only for the last 5 years that the lamp was worth more than 15,000. So it sure feels intuitively like the actual true average value of the lamp is going to be a lot less than $15,000. So make your best guess. I don't know, 10,000, 5,000. I'm just kind of looking at like where's the like basic middle of this curve thing. I'm just going to guess $6,000. Let's see how close we get. So now we're going to use calculus and technology. So here we go. The formula for average value is right up there. 1 over b minus a times the integral. So here's the integral. 1 over 35 minus 0. Don't forget that part. I guess I should call this b average. Times the integral from the same 0 to 35 of the function. Let's make sure we got that right. Yep, good. So we're just going to type this into the calculator. Okay, here we go. So I'm going to do 1 divided by 35. And then I'm going to multiply by the integral right here, math 9, 2.25 times 1.15 to the x, comma, bottom number, comma, top number. All right, so the average value, what is that? That is not what I was expecting. 1/35, 2.25 times 1.15 to the x, comma, 0, comma, 35. Let's pause and reassess. Okay, I see what I did here. I had a 2.25 there for some reason. It should have just been 225. Whoops. Okay, so that's just going to move the decimal point in our answer 2 places to the right, but let's just fix that right here. So the average value over the course of this 35-year period is about $6,079 and change. $6,079.22. Let's erase that errant decimal point. Okay, so that is the average value. It's perfectly reasonable it's definitely less than 15,000, just looking at how long it took to get to that 15,000 halfway point. Okay, common wrong answer for average value questions is to just do the integral and forget to do the 1 over b minus a. Okay, next part, pause and read the question if you haven't done so. First, what are the units for integral 1960 to 1970 of g of t dt? What does it measure? So the units, remember, are going to be the g units times the t units. G, according to this problem, is measured in trees per year. Trees per year times the t units, which is measured in years. So the ultimate final unit for this integral is trees. What does it measure? Well, g of t is a growth rate, and we know that when we do an integral of a growth rate, we are finding the change in the original function. So it is going to measure change in not the rate of trees, but the actual number of trees. Number of trees between 1960 and 1970. What's the smallest possible value of that integral, and then the largest possible value? Okay, so we know that the function is increasing. That's important here. And so between 337 and 371, if we're looking for the smallest possible value, we could assume that for the entire 10-year period, 1950 to 1960, that it was actually 337, constantly 337 for the entire 10 years until the last second of the last day of 1959, when it just miraculously jumped up to 371. So let's assume it was 337 for those 10 years. So for our smallest possible one, it's going to be 337, that's 337 trees per year, but times 10 years. It's not just 337 because it's a 10-year period. You can think of this thing as being the area of a rectangle, base times height. 337 is the height, 10 is the base. Or you could think of it as like our velocity curves. It's a velocity times time. 337 in some sense is the velocity of the trees, and 10 is the number of years, it's the time. So velocity times time, or height times base. Plus, and then in the next 10-year period, 1960 to 1970, you're going to pick the smaller of those two and just assume that it stayed at 371 the entire 10 years, so 371 times 10, and then we just keep going this way. Make sure you don't get carried away. You do not put the 493 in this lowest estimate, because from 1980 to 1990, we were looking at 448, and that's the end. That's the last 10-year period. So we do that calculation, and then separately, you can do the largest possible value. In this 10-year period, which number are you going to pick? We're going to pick the 371, the largest one, overestimating, times 10 years, plus 408 times 10. And then finally, plus 493 times 10. The 493 does get into this one, but the 337 does not get into that one. So they each miss one. Green and red both miss one. Okay, so you do the calculation. I'm just going to read it off of the key here. So 3710 and 4080. Okay, so those are our two estimates for how many trees, how many new trees, or how many trees got added between 1960 and 1970. Definitely more than 3,710 and definitely less than 4,080. Would your answer to B still be correct if the number of new trees per year wasn't increasing? No, it wouldn't be, because, for example, if we didn't know that we were increasing in this 10-year period here, then maybe it started at 337, but then the very next year it dropped way down to like 200, and it stayed at 200 until 1959, and then only in the last year did it jump way back up to 371, in which case this calculation would be too big. It's definitely not too small in that case. So we need the growth rates to be increasing in order for us to have done this calculation. Okay, and then the last one, give your best possible estimate. So I guess our best thing is to average the green and red numbers. So 3710 plus 4080 divided by 2, which turns out to be 16,420. What am I looking at here? Averaging this. Did I do something wrong? 4080, 3710. Yes, totally did something wrong. Okay, so back up here, I was actually answering a question from for the number of trees between 1950 and 1990. I was kind of thinking of this question already, and that is not what these questions were asking. These were specifically asking just between 1960 and 1970. So I should have only done one calculation instead of all of these calculations. So before I erase all of that and hide my mistake, I'm going to use those numbers to answer this part down here. So the 3710 is no good. I was reading an answer off the answer key, which of course is absurd. 3710 is this number. It is definitely not the sum of those four numbers. 4080 was just this one number. So let's do this calculation here. So we got 337 times 10 plus 371 times 10 plus 4080 plus 4480. I have that right? 4480. Yeah, that looks good. Okay, 15,640 is an underestimate for the part D. And then we'll do the thing over here with red. 3710 plus 4080 plus 4480 plus 4930. Some of you smarty pants might recognize there's a lot of overlap between these numbers, and so maybe you could subtract a single number from this thing and add in a single number to get this. I'm not that smart. I've been in this room for like 7 hours straight, lecturing to an empty classroom. So let's use those numbers, but first hide some of this evidence from my goof. Okay, so we didn't need that. We only needed the thing in the middle, and that was 33,710 trees there. And again, for the red, we only needed 408 times 10 equals 4,080 trees. Okay, so I think that part is good now. And then we can come down here and write this calculation again using all of the work on the calculator. So 15,640 plus 17,200 divided by 2 equals 16,420. So explain its meaning. That means that's our estimate for the number of additional trees, number of new trees between 1950 and 1990. Okay, good there. All right, we know f of 0 is 10 and f prime is given by this graph. We're going to find the values of f by looking at the area between the derivative and the x-axis. This is identical to the stock market example. It just doesn't have the stock market words associated with it. But let's go ahead and start calculating areas. First area is 0 to 1. So you could do trapezoids, or you could cut it into rectangle and triangle. The area of the rectangle is 2 times 1, which is 2. Area of the triangle is half of 1 times 2, so I think that's a 1. So 2 and 1 is 3 altogether there. I think I'm actually just going to go through and calculate these areas before putting them all together in the big table. Okay, next up is this triangle right here. Half the base times height, half of 1 times 2 is 1. Let's do the next one. It's up here. Make sure you're on the correct side of the curve. It's always between the curve and the x-axis. Okay, half base times height, that's just a half. We'll cut this one into two. The triangle is the same. The green triangle at the top is the same as the blue triangle. So that's a half plus a 1 by 1 square. So that's a 1.5. Next one is this one. Even in my tired state, I can't mess up a rectangle. That's a 1 times 2. 2. Okay, and then finally, we run out of colors. No, one more. This purple triangle, half of 1 times 2 is 1. Okay, so let's put all of these things together into our chart. Now, those things all represented the actual amounts of change. Those areas represent actual change in the original function capital F. In the original function capital F, we are told starts when x is 0 with an output of 10. So we're going to start with the 10. This orange thing is a 3, but it's below the axis, so that means we lose 3, so we went from 10 down to 7. The red thing, red triangle is a 1, but it's below the x-axis, so we lose 1 from the 7 we had, and we get 6. The blue triangle is above the x-axis, so that's a positive 1/2. We had 6, now we have 6.5. The green is a positive 1.5. From 6.5, we go up to 8. Black 2 is positive. We go from 8 up to 10. And then the purple is a positive 1, up from 10 to 11. Okay, that's it for number 5. Suppose that f is a function with f of 0 equal to 1 and f prime equal to 12 minus 3x squared. Part A, use your calculator to find f of 1. Hint, fundamental theorem. Okay, so we know that the integral from 0 to 1 of f prime of x dx is f of 1 minus f of 0. We also know that f of 0 is given to be 0 in this problem. And this integral is something that we can type onto the calculator. And so as soon as we type this, need parentheses here because it's more than one term. As soon as we type this on the calculator, we'll be able to calculate f of 1. So let's do that. Okay, so we're going math. Nope, math 9. All right, and the function is 12 minus 3x squared, comma, x, comma, 0, comma 1. So that's an 11 on the left-hand side there. 11 equals f of 1 minus nothing, therefore f of 1 is 11. Great. So then we're going to use the same method as we did in part A. So let's do, I'll write one more in terms of details, and then you can do the others on your own. So we're going to do the integral. You could do the integral from 0 to 2, but I'm actually going to do the integral from from 1 to 2 of the same function. And according to the fundamental theorem, this is really f of 2 minus f of 1, always top minus bottom. F of 2 is what we're about to find. F of 1, we just calculated, is 11, and the integral is a tricky area, but the calculator is going to be able to take care of that for us. So this is now the integral from 1 to 2. And that integral is 5. And so then we just add the 11 to both sides to discover that f of 2 is 16. And that's it. So we just do that same idea for the other 3 pieces. So I will, I'm not going to write it, but I'll at least do the calculations here on the calculator so you can see. So the next one we're going to go from 2 to 3. So that's a negative 7. So negative 7 is supposed to be here. This is not 11 anymore. This is now going to be a 16. So we're trying to get from, so we know that f of 3 minus 16 is supposed to be this number right here. So what number minus 16 gives you that number? It's got to be a 9. I'm sorry if that's confusing because I didn't write it, but really you can just pause the video and write it out and you'll see. Okay, and then the next one, we're going to go 3 to 4. Negative 25 equals some number minus 9. So add the 9 to the other side. Negative 16 is what we should get. And then one more. From 4 to 5. Negative 49 is some number minus negative 16. So that really became a plus. Maybe I should write this one just because it's negative. So negative 49 for that one. Negative 49 is f of 5 minus negative 16. So that becomes a plus 16, which you move to the other side by subtracting it, and you get negative 65. Okay, then it says try to find a function f whose derivative is 12 minus 3x squared. Why are we doing that? Well, I think it's actually written on the next page. Nope, it's on. Why are we doing that? Well, take a look at what we had here. So we said we were going to think of f as being some function whose derivative is 12 minus 3x squared. And we intentionally called it a derivative so that we could use the fundamental theorem of calculus part 1. Well, somebody took a derivative of some function and got 12 minus 3x squared. Let's see if we can go the other direction. F of x equals, maybe, okay, someone whose derivative is 12 minus 3x squared. Now I like that subtraction sign because that meant somebody took the derivative of two separate things with a subtraction sign in between. So we can separate those in our own minds. So let's just focus on 12. Whose derivative is 12? Well, I know that 12 times x has a derivative of 12. And then the minus must have come from a subtraction in the original function f, and then 3x squared. I've seen that before. Some function whose derivative is 3x squared. Oh, I got it. It's just x cubed, right? The derivative of x cubed is 3x squared. So if you check my work and take the derivative of that blue function, you get 12 minus 3x squared. Excellent, excellent, excellent. Okay, some of you might say that there's another answer or infinitely many other answers, and you are right. This is the one we're going to use. We're not going to get into the details right now for why it's this one and not one of the infinitely many other answers, but we're moving on here. And then it says evaluate f, this particular function f, at 0, 1, 2, 3, 4, and 5. We'll do a couple of these by hand, and then we'll do the rest on the calculator. Okay, so plug 0 in for both of these x's. We're going to get 0. Plug 1 in, 12 times 1 minus 1 cubed. 12 minus 1 is 11. Plug 2 in, 12 times 2 minus 2 cubed. 24 minus 8, that's 16. And then we'll do the other ones on the calculator, 3, 4, and 5. 12x minus x cubed. Just check my work here. So 0, 1, and 2. Yep, we get exactly what we said. And then 3, and 4, and 5. 9, negative 16, negative 65. That is interesting. Those numbers sound familiar to me. 9, negative 16, negative 65. Do I have those right? 9, negative 16, negative 65. Okay, let's see. So this was f of 3, and 4, and 5. So why do those numbers sound familiar? All right, the collection is 0, 11, 16, 9, negative 16, negative 65. Oh my goodness, look at that table. Reading right across here. 0, 11, 16, 9, negative 16, 65. And in fact, isn't f of x exactly what we were calculating, right? We didn't have a formula for f, but we were using this crazy area under a derivative idea to get isolated values for this unknown function f. But then somehow we had this antiderivative miracle here, and then we plug in and we got the same exact numbers in the chart. That is a lot of what we're going to be doing at the start of Calculus 2.